Hello, we're going to start talking about chapter 2. And chapter 2 is pretty dense, but just realize that it's an introduction to a lot of new ideas if you haven't studied a lot of chemistry. But over the block, you'll learn a lot of the material in much better detail than you're learning here. So it's really just to introduce some new terms and get you used to talking about chemistry. I'll try to point out some things that will help you focus a bit on what you want to learn. So let me get my screen. Okay, so we're talking about atoms, molecules, and ions. And so I'll do this in 2 sections because it is a long chapter. So I'll go through radioactivity and then we'll take a little break. So you don't ever have to memorize any symbols or names. What I'll give you in class is a periodic table. On the front, it's just a periodic table, and on the back, it gives you the symbol and the name for each of the elements. So you'll always have that on the test. This is just to get you thinking about some of the names and how things are named. Oftentimes they're Latin names. Oftentimes with newer elements, they're named after people or the city that it was discovered in, like there's one named after Berkeley. So this is just to get you start thinking that we have elements, which we're going to learn a little bit more about what that means to say you have an element. And then each of them is given a symbol, so it's easy to write what element you're talking about. So this is the type of periodic table I'll give you, and we'll spend some time. You can write on it, and you can help yourself organize and always bring it to the test. So each element has an atomic symbol and an atomic number. So the symbol is just the abbreviation for what element it is, and the number we're going to see tells us how many protons are in that particular element. So hydrogen is H, it has a 1, which means it has 1 proton. Helium is 2, and He, and it has 2 protons, etc. So you don't have to memorize these things, but as you look at the periodic table, there's an organizational pattern to it. Mendeleev came up with this idea. And over time, now we understand why there's this periodic trend, why we have rows which are called periods and columns which are called groups. And this is just telling you how many of each of those are. It's not really an important thing to know how many. You'll always have the periodic table, but a horizontal row is a period, a group is a column. We're going to see groups are super important in that they have similar behavior. So we'll think a lot about that. So we have the main groups in columns, we have transition metals, and we have inner transition metals. So when we go back here, the main groups are the 2 columns on the far left and the 7 columns on the far right. The transition metals are that area in the middle, and the lanthanides and actinides are at the bottom. Those are the inner transition metals. So think about the elements. The important thing is the periodic table is a way of organizing the elements so we understand their properties and some of the relationships between properties. So we'll be thinking a lot about properties. So this may seem random, but just a couple definitions. An intensive property is independent of the sample size. So for example, if you're measuring temperature or the point at which an element melts, it doesn't matter how much you have, it'll have the same temperature and melting point. But then there are other properties that do depend on the size of the sample. So things like length, volume, mass, we'll look at lots of them. So within the periodic table, we'll be understanding why changes take place. So physical changes are characteristics that do not involve a change in the sample's chemical makeup. So that's something like boiling water, having it go from the liquid to the gas, or freezing salt, having it going from a liquid salt to a solid salt. So those changes will depend on what elements make up your sample. Chemical properties are characteristics that do involve a change in a sample's chemical makeup. So it'd be something like burning a fuel. You take the fuel, you add some oxygen, you end up with carbon dioxide and water. We'll learn about writing chemical reactions later, but where you actually have a change, you start out with some substances, in this case compounds, and end up with different ones. So these are just more examples in the table of physical properties and chemical properties. So temperature, color, melting point, those are all things that are physical properties. Rusting is a chemical reaction. Combustion of a fuel could be gasoline. Tarnishing of silver, cooking an egg, those are all things that change the actual way atoms are held together in different structures. And we'll learn a lot about that process of a chemical reaction. Some of the properties of the elements. So when you look at the columns, as I said, a column is a group. The first column on the left is the alkali metals. And we'll see that there's a lot of similarity in that group that's colored here in pink. So when you look at lithium and sodium, for example, and potassium, which are all in that group, you always find them within salts with a +1 charge, which means they're going to be cations. And so that's a similarity. And so that's why the periodic table is arranged the way it is, because Mendeleev saw these similarities and put elements with the same characteristics into groups. And it turns out when we look at how the atoms are constructed, so what their electrons look like, we'll see that there's a reason why they end up in these groups. They have similar properties in their electron structures. So alkaline earth metals have similar properties, the halogens, which are on the far right, and then also the noble gases. So a column is a group, and those elements within those columns have similar properties. This is just thinking about naming, and you'll be able to put this on the periodic table that you bring to the test, so you will not have to memorize something like this. But all the elements on the far left, except hydrogen. Hydrogen is 1A. It's that first element in the upper left-hand corner. And hydrogen acts like an alkali metal and like a noble gas. So we'll have to think about why that is as we learn more about hydrogen. So everything on the left and at the bottom of the table is considered a metal, and that will have, they all have similar properties. Everything in the upper right-hand corner is called a non-metal. And you see some pictures here of some of their properties. They're often colored. They can be gases, they can be solids, they can be liquids at room temperature. And then on the line that separates the non-metals in the upper right and the metals on the left, we have what are called semi-metals, things that act sort of like metals and sort of like non-metals. So we'll learn about some of their properties too. So conservation of mass and the law of definite proportions. It's really quite common sense. Within a chemical reaction, so at the bottom of this, we have mercury 2 nitrate, and we have potassium iodide. We're going to learn how to name these as we get to the end of the chapter. And it makes mercury 2 iodide and potassium nitrate. In that reaction, what you see there is that the elements are within compounds, but they're just arranged differently. So the mercury on the left is with the nitrate, the mercury on the right is with the iodine. So this is an example of a chemical change where you're changing from one compound to another as you go from the left to the right. And so when you look at this, if you add together all of the mercury 2 nitrate and the potassium iodide that reacts, and then you add together all of the mercury 2 iodide and the potassium nitrate that you make, those two numbers have to be equal to each other. And that's just the law of conservation of mass, that mass is not created nor destroyed if it's just a chemical reaction. The conservation of mass and the law of definite proportions. So this is just going through that again, showing you it in a visual, but it's exactly the same equation at the bottom. So the law of definite proportions tells us that every compound has the same number of different atoms in it. So for example, we have water, the compound named water. It will always have 88.8% by mass oxygen and 11.2% mass by hydrogen. There'll be no other mass ratio that gives you what's called water. So different samples of a pure chemical substance always contain the same proportion of elements by mass. The law of multiple proportions and Dalton's atomic theory. So number one, law of multiple proportions. Elements can combine in different ways to form different substances whose mass ratios are small whole number ratios of each other. So when we have something called nitrogen monoxide, which is a single nitrogen atom with a single oxygen atom, the ratio of the masses will be 7 grams of nitrogen per 8 grams of oxygen. But nitrogen and oxygen combine in other ways too. You can have 1 nitrogen atom and 2 oxygen atoms, then it would be called nitrogen dioxide. And in that case, you have 7 grams of nitrogen, but 16 grams of oxygen. So when you look at that as a ratio, you have twice as much oxygen per gram of nitrogen in the nitrogen dioxide as you do in the nitrogen monoxide. And so the law of multiple proportions says that makes sense, that the ratio should be a simple whole number ratio, and the ratio is 2. This is just showing that in a visual. Like I said, nitrogen monoxide is 1 nitrogen atom combining with 1 oxygen atom to make nitrogen monoxide as a covalently bonded molecule. And if you make nitrogen dioxide, you have twice as much oxygen. Also, each of those together, 3 of them make 1 molecule nitrogen dioxide. So what you can get from this, so Dalton's atomic theory, which, oh gosh, I feel like this was at the end of 1800s, where he's coming up with are ways to explain the definite and multiple proportions. And so one of the ideas he came up with, that elements are made up of tiny particles called atoms. And so that would make sense. If water always has the same mass ratio of oxygen to hydrogen, it always has the same amount of hydrogen and oxygen. And so if it comes in small particles, that makes sense that you can't break a particle, for example, of hydrogen or oxygen into something smaller. So for water, it has 2 hydrogen and 1 oxygen. And the hydrogen and oxygen are tiny particles called atoms. So each element is characterized by the mass of its atoms. Atoms of the same element have the same mass, but atoms of different elements have different masses. And we'll see that's not totally right, but this was Dalton's atomic theory. We'll see when we have something called an isotope, an element can have a different mass, and we'll understand that here in a minute. So the chemical combination of elements to make different chemical compounds occurs when atoms join in small whole number ratios. So that makes sense. You have to take a particle of hydrogen, a particle of oxygen, combine those together. You can't combine half of a hydrogen or half of an oxygen. Chemical reactions only rearrange how atoms are combined in chemical compounds. The atoms themselves don't change. So with Dalton's law, or Dalton's theory proposed, scientists wanted to know more about what atoms really are. And so J.J. Thomson was the first one to look at what an electron is. And he created this thing called a cathode ray tube. So it's an empty tube you see in this picture. And on each end, you put in a metal electrode, something that can carry electricity. And if you hook 2 leads up to that and hook them up to an electric circuit, you can pass electricity through this hollow glass tube. And when you do that, what you see is that those cathode rays in there are actually tiny negatively charged particles, and they called them electrons at that point. So if you look on the right, you see that when you put a magnet there, you can bend that ray. And so electrons, which are negatively charged, can interact with a magnetic field. So once you know about electrons, you want to know more about what they are. So this is Mulliken's oil drop experiment. So the first thing he did was the oil drops that he sprayed in this box, and we'll see what else is in the box as we talk about this, they're allowed to reach their terminal velocity. So that means they're allowed to fall with gravity. And by doing that, you can figure out the mass of each drop. And so once you know the mass of each drop, you can figure out the charge on each drop. So the falling oil droplets are given a negative charge by using X-rays. And X-rays can take electrons off of atoms, and so you can leave behind a positive charge. Whoops, no, they're given a negative charge by X-rays. Not sure how that works. I'll have to think about it. And they're suspended though, so whether it's a positive or a negative charge doesn't matter so much. Just matters that once those oil droplets are charged, you can interact with them with an electric field. And so if you look at the two plates inside the box, if you put a charge of plus on one and minus on the other by using an electric circuit, you can continue to increase that positive negative charge until the oil droplets are just standing there and they don't fall anymore. So from that, you can calculate the mass of the drop and the voltage on the plate. Whoops. So you can calculate the charge on the drop by calculating the mass, which you had from the first experiment, and then the voltage on the two plates. So once you have the mass to charge ratio, we can figure out the charge. So the electrons we learned over time are surrounding the inner part of the atom, which is called the nucleus. And so Rutherford determined that the nucleus is really tiny and that most of an atom is really just empty space. So he did this by bombarding a gold foil with alpha particles, and most of the alpha particles pass through the foil undeflected. Approximately 1 in every 20,000 were deflected. So that means it looks like they interacted with something in that gold field. So a fraction of those particles were deflected back at an extreme angle. Rutherford proposed from this that the atom must consist mainly of empty space, therefore most of the particles just go right through, and that the mass is concentrated in a tiny central core, and so that every now and then the alpha particle interacts with a nucleus. And if you look at this picture, that just makes it more visible. So on the right, if you look at the gold foil, it's really mostly empty space. And so if you shoot electrons from the left through to the right, in general, what you see is that the electron doesn't, or that the alpha particle does not run into a nucleus. And an alpha particle is a charged positive particle. So if an alpha particle were to run into a nucleus, they would repel each other. But the first 3 electrons at the top, or the first 3 alpha particles, go straight through. But then this 4th one, you notice, randomly does hit that nucleus, which is not a very probable event. And it's a little bit deflected because it doesn't hit right center on. The next one goes all the way through. The next one hits more head on and it does bounce back. And so depending on how you hit that nucleus, it could either be slightly deflected or it could bounce all the way back. But what Rutherford really demonstrated with this is that the nucleus is very small and you're not very likely to run into it. Most of the atom is empty space, and that the charge on the nucleus is positive because an alpha particle in this experiment on the left is interacting with a positive nucleus because an alpha particle is positive in order to have these kinds of behaviors. This is just a picture showing you how much empty space is in an atom. So it's often used as an example. If you had a pea in this stadium, that would be the size of the nucleus, and the entire rest of the volume of the stadium would be the volume of the atom, and the pea was all that the nucleus took up. So with all of these experiments, we learned the mass and the charge on all the particles. So an electron is very light. On the left, it's boxed in how light it is. So in grams, 1 electron is 10 to the minus 28 grams. Protons and neutrons are very similar in mass, and they're about 2,000 times as heavy as an electron. If we look at the charge on an electron and a proton are equal and opposite. So an electron is -1, a proton is +1, and a neutron has 0 charge. It's a neutral particle. So when we start now explaining or labeling the characteristics of the atoms within an element, the atomic number, which is given the symbol Z, tells you the number of protons in an atom's nucleus. It's also equivalent to the number of electrons around the nucleus, because in order for that atom to be neutral, the proton and electron number has to be equal in order for those two charges to add up to 0. The mass number A is the number of protons and the number of neutrons in the nucleus. So notice the protons and neutrons are very, very heavy. They make up most of the mass of the atom, and they are always in the nucleus. So the mass number tells you the total number of nucleons, they're called, protons plus neutrons. And an isotope, which I mentioned earlier, atoms of the same atomic number, so they have the same number of protons, but they have different mass numbers, which is the same thing as saying they must have different numbers of neutrons. This is just pointing out hydrogen is kind of unique in that you give the different isotopes different names. So protium on the far left is just a single proton, has no neutrons, and so the mass number is 1. Deuterium is the second isotope of hydrogen, has 1 proton and 1 neutron, so its mass number is 2. And tritium has 1 proton and 2 neutrons with a mass number of 3. So when you want to label that or show the number of protons and neutrons, you put the atomic symbol in the middle. So here it's carbon for each, but carbon 12 and carbon 14 are 2 different isotopes. So in the top one, you have 6 protons, 6 electrons, and 6 neutrons, because the mass number adds up to 12, and 12 is equal to the proton plus the neutron number. So 12 as the mass number minus 6 protons tell you you have 6 neutrons. That's the most common isotope of carbon. But there's another isotope of carbon, which is also exists in the atmosphere. So it has a mass number of 14. So notice it has the same number of protons and electrons as carbon 12. That will always be the case, but the neutron number will be different. So the atomic number is always the same. The mass number will be different for 2 different isotopes. So in the lower one, we have 8 neutrons. So when we think about the mass, it's important to realize that if you have different numbers of protons and neutrons, you're going to have different masses for each element. So by definition, we say that the mass of one atom of carbon 12 is defined to be exactly 12. And so when we look at the atomic mass at the bottom on your periodic table, the atomic number is at the top, the symbol in the middle. But the atomic mass here of 12.011 shows you that when you take a sample of carbon out of the atmosphere, it's not all carbon 12. So if it was all carbon 12 and we had defined the mass of one atom of carbon 12 to be 12, then the atomic mass would be 12. But you'll see from this atomic mass that a sample of carbon naturally occurring on planet Earth has some higher isotopes, has some carbon 13 and a little bit of carbon 14. And so this is just showing you that idea. So if a sample of carbon is mostly carbon 12, this says it's 98.89% on Earth, and it's 1.11% of carbon 13. If you just do a weighted average of those two, you end up with 12.01. So you have 0.9889 is the fraction that's carbon 12. So that's on the left. And 0.0111 is the fraction that's carbon 13. And so when you multiply and add those together, you get 12.01, which is has 1 less sig fig, but that's what the periodic table shows you. So the other thing about mass is if we define the mass of carbon to be exactly 12, and that's in atomic mass units, then everything has a mass relative to that. And so Avogadro's number was come up with because if you want to know how many atoms are in a sample of something, Avogadro's number is the number in a sample that's in grams for its atomic mass. So 1 mole of a substance contains 6.022 times 10 to the 23rd formula units. So that's Avogadro's number, 6.022 times 10 to the 23rd. The molar mass in grams of 1 mole of any element. So if you look back at the periodic table, and if you were to take 12.011 grams of carbon, you would have a mole of carbon. And a mole of carbon is Avogadro's number. So it's the same as saying you'd have 6.022 times 10 to the 23rd carbon atoms. So it's numerically equivalent to its atomic mass. So now we're going to talk just briefly, and then we'll take a break, about nuclear chemistry. So that's when one element actually changes into a different element. So this isn't a chemical reaction, this is a nuclear reaction. So the equation that represents, for example, in the upper atmosphere, carbon-14 can become nitrogen-14. And in that process, you lose an electron from the nucleus. And, well, we'll think about how can you lose an electron from the nucleus if there aren't electrons in the nucleus. Turns out if a neutron falls apart, it can become an electron and a proton because you have to conserve charge. So it can become a plus charge for the proton and a negative for the electron. So this electron is coming out of the nucleus, but it didn't exist there. It's a result of a neutron falling apart. So notice on the left and right, you have different elements. So we know that this is a nuclear reaction. Nuclear chemistry, the change of one element into another. So if you compare a nuclear reaction to a chemical reaction, a nuclear reaction changes an atom's nucleus, usually producing a different element. A chemical reaction, by contrast, involves only a change in the way the different atoms are combined. So you may have water on one side of a reaction. On the other side, you may have hydrogen and oxygen. That's a chemical reaction because it just changes how the elements are arranged in the compounds. Different isotopes of an element have essentially the same behavior in chemical reactions, but often have a completely different behavior in a nuclear reaction. And we'll learn a lot about that as we go through the course. The energy change accompanying a nuclear reaction is far greater than that accompanying a chemical reaction. So a chemical reaction where we get energy is something like burning gasoline in your car. A nuclear reaction is a reaction like using uranium-235, and it undergoes fission in a nuclear reactor in order to make electricity. And you need a lot less uranium to make the same amount of energy as you need gasoline. So that's because nuclear reactions give off a lot more energy. So a lot of elements are radioactive. So when you look at carbon-14 and nitrogen-14, they're radioactive, which means they decay. They don't stay around a long time. So how do elements decay? So in this case, it gave off electron. That would be called beta decay. So beta radiation is strongly deflected towards the positive electrode. So you can tell what particles are coming off. So over on the left, if you have a radioactive ball of material here, and it's being shielded with a big metal chunk so that if you're standing there, you're not getting the radiation. If it gives off beta particles, you'll know because if you have your electric plates here, one positive and negative, electrons will go towards the positive side because they're negative. Gamma radiation, which we'll see is just light, is undeflected, so the green rays come straight through. And alpha particles, because alpha particles are helium nuclei, so they're positively charged, those alpha rays will be deflected towards the negative plate. So Alpha radiation. An alpha particle is just a helium nucleus, so it has 2 protons and 2 neutrons. So this is an example of the natural radioactive decay of uranium-238, which is the primary isotope of uranium if you took a rock out of the ground. But it decays, takes a long time for this to happen. But when an alpha particle is given off, so the alpha particle is that helium-4 isotope, when that comes off, it leaves behind thorium. So the way you can balance these, because you can't balance them for elements, is to realize that the mass number in blue has to be equal on each side. So on the left-hand side, you have 238 mass particles. And if you add together the 4 from the helium and the 234 from the thorium, you'll have 238 particles on the right-hand side too. You also have to be able to balance the charge, so you can't create or destroy mass or charge. So the red on the left-hand side and right-hand side have to be equal. So this says that you have 92 protons on the left-hand side. Those are each positively charged. And on the right-hand side, helium has 2 protons and thorium has 90. So that adds together to be equal to the 92. Beta, like I said, is where one of the neutrons actually changes into a proton and an electron. So you have to balance it in the same way. Iodine-131 is a radioactive isotope of iodine. And so on the right-hand side, the mass has to be the same. So you have 131 mass particles in the xenon. And electrons are so much lighter than protons and neutrons that they essentially take away 0 mass. They don't have any nucleons. And so 131 equals 131 plus 0. And then same is true for the charge, but now we want to think about if you have 53 positive charges on the left-hand side, one of the neutrons in the nucleus goes up to a proton. And so on the right-hand side, now you have 54 protons, but you have the same number of nucleons because one of the neutrons just became a proton. And then the electron has a -1 charge. And so -1 and positive 54 adds up to positive 53. So it doesn't matter what particle comes off, you're going to balance nuclear reactions in the same way. Gamma radiation is just light. It's higher energy than X-rays, and so, but it's just a photon of light, which means it doesn't change the mass or the charge of your sample left behind. A positron is an electron with the opposite charge. So if you see on the far right, the positron has 0 nucleons, but it's the same charge except opposite sign. So a beta particle would have a negative sign, a positron would have a positive charge. And so sometimes it's written as beta positive because beta represents an electron. And if you change it to beta positive, it has all the same properties of an electron, except it has a positive charge. I'm going to balance it exactly the same way. 40 on the left, 40 on the right for number of nucleons, 19 on the left, and 18 plus 1 gives you 19 on the right for the total number of positive charges. Electron capture sometimes happens if you think about an atom. If you have a really big atom, some of the electrons are really close to the nucleus in the inside of the atom. And if that nucleus has a lot of positive charge, it can actually suck an electron into the nucleus, essentially. And so when it does that, an electron can't exist in the nucleus, but it can be absorbed by a proton and converted into a neutron. And so electron capture means the electron is on the reactant side. Charges all have to balance the same. 197 plus 0 has to equal 197 on the right-hand side. And 80 minus 1 means that we now only have 79 protons in the gold that's created in this electron capture reaction. So this is just a summary, and you'll get a note card for each of your tests, which means it might be really helpful to put this on a note card. Just tells you the properties of each particle. An alpha particle is the helium nucleus. It's given the Greek symbol alpha there. Charge or change in atomic number goes down by 2 when an alpha particle leaves. The mass number goes down by 4, and the change in the neutron number goes down by 2. So you could summarize what we just went through with this little table on your note card if you find that helpful. So I'm not going to focus a lot on stability, but just to think about why elements exist in the isotopes they do. The blue band on here represents some stable isotopes. The red line is a line where the neutron to proton ratio is 1. So you see that most stable isotopes are pretty close to 1, and so that blue area is called the band of stability. It's not exactly 1, but it's close. So every element in the periodic table has at least one radioactive isotope, and hydrogen is the only element whose most abundant isotope contains more protons than neutrons. It has a proton and a neutron. The ratio of neutrons to protons gradually increases, giving a curved appearance to the band. So it's starting to curve upward as you get more neutrons per proton. So I'm not going to ask you any of these questions on a test or anything, but it's interesting to understand what we know about what isotopes are stable. All isotopes heavier than bismuth-209 are radioactive. Even though they might decay slowly, they could be stable enough to occur naturally, but they will decay over time. This is just showing you, and you can look at this and put some thought into it, but when you're above or below that band of stability, you're either going to want to gain negative charge or positive charge. So you're either going to want to give up protons or gain protons in the nucleus. So this is just showing you what's going to probably happen. So nuclei that have higher neutron to proton ratios tend to undergo beta emission, because if an electron's given off, you're essentially creating a proton. So you're going to make that neutron to proton ratio smaller. And so you can just look at this and realize that there's a reason why we have beta, alpha, positron emission, or electron capture. Because of that desire to become closer to a stable isotope. We're going to take a break there and come back and talk a little bit more about naming chemical compounds. So, be it for now. I'll be back soon.